In this video, we're going to look at trigonometric integrals, as in just integrals that have a whole bunch of trig expressions inside of them. And the basic methodology here, if you can even call it that, is you take some integrand that you don't know how to integrate, you don't see some obvious u substitution, for instance, and you apply a bunch of different trig rules. The trig rules convert it, and now it's of some form that you know how to do. Maybe you could apply a u substitution after you have applied some trig rules. So, for instance, in this example, we have cosine of x times cosecant squared of x. And I don't immediately, when I look at this, see some u substitution that I want to do. For example, I don't want to have u as cos, doesn't really make any sense. U as cosecant of x. Those may be reasonable guesses, but if you try them, you're not really going to get anywhere. So we want to apply a trig rule. And for this one, we don't have to apply that much more complicated of a trig rule than just the definition of cosecant of x. So what I'm going to do here is I'm going to realize that cosecant is 1 over cos. So, 1 over sine. So this is going to be equal to the integral of cosine of x. I haven't changed that at all. And then cosecant squared is the same thing as 1 divided by sine squared x dx. So I just applied a very simple trig rule. In fact, it's just a definition. Now, when I look at it in this way, things are going to become a little bit easier because I can now start to recognize that I have a derivative pairing in there. In particular, cosine is the derivative of sine. So now that I have it written down here, I can think of cosine as the derivative of sine. Why don't I come and set my u equal to sine of x? Then my du is going to be equal to cosine of x dx, and this allows me to do a bunch of substitutions inside of the integral and gives me simply cosine x dx. I have a du on the top, a u squared on the bottom, and now this is something I know how to do. This is just going to be a normal old power rule, and so I'm going to say minus u to the minus 1 plus c, and our implicit agreement is always going to be that when we're doing a u substitution, we do not leave it written in terms of u. We take that final step and re-substitute in the u minus sine of x all to the power of minus 1 plus c. And I put these big brackets around here just so that we're not confused. We don't think it's the inverse sine or arcsine of x. Okay, so now I have a little bit more complicated of an integrand. It still has trig inside of it, but if I look at it, there's not any immediate obvious u substitution that are screaming out to me. The derivative of, say, tan is not sec to the 4th, or the derivative of secant isn't tan cubed, so nothing sort of cleanly works in terms of an obvious u sub like that. And also, if I was to convert this, for instance, just to sines and coses, well, tan would go to sine over cos cubed, and then secant is 1 over cos, so it would kind of be like sine cubed over cos to the 7, I don't really see how that's helping me. So the trick that we did before, which was just use the definition to turn it to sine and cosine, doesn't appear to be all that helpful here. But I know a whole bunch of other trigonometric rules that I could possibly apply. So let's look at a couple of them, and then we'll come back and see if any of them might be valuable in this case. So that's actually going to be our big goal, is to find these other trig expressions and have those trig expressions make our original function, or original integrand, easier and more amenable to finding a u substitution. Okay, so here's a couple of the ones that we might want to have. These are the 3 different Pythagorean identities. You can think of them as separately and memorize them all 3. I actually never do that. I only go and memorize the first of the 3. The sine squared plus cos squared is equal to 1. And then for the other ones, what I do to get down here is just, this is 1 divided by cos squared of x. See how sine squared divided by cos squared is tan squared, cos squared by cos squared is 1, and 1 divided by cos squared is secant squared. And then this one down here, that is me doing 1 over sine squared of x. So I only really ever memorize the first Pythagorean identity and just derive the other 2 when I need them. A couple other ones that are going to be useful that you should also sort of have in your memory banks are the half angle and double angle identities. These are ones that allow you to take either products of sine or products of cosine or one sine and one cosine and convert them down into something else. So sine squared gets related entirely in terms of cosine 2x and this half factor. Same for cos squared. Same for sine of x times cos of x. All of them become a little bit simpler on the right-hand side. And the key point I want you to note here is that the right-hand side I know how to integrate. I know how to integrate 1/2 of 1 minus cos 2x. Cos 2x is a really easy u substitution. It's just u equals 2x. And of course I know how to do the integral of a constant. Same for 1/2 sine 2x. Again, the right-hand side are easy to integrate. The left-hand side are complicated. If I didn't know these identities, I wouldn't know how to do sine squared. So these half angle and double angle identities are really useful for simplifying trigonometric expressions. Okay, so let's go back to our one that we didn't know how to do. Maybe one of these ones that we've seen are going to be useful. So what was I at? 10 cubed times secant to the power of fourth. Now, I remember something about secants. Let's recall ourselves. I'm going to scroll back and look what it is. Yes, it was this one right here. I have the tan squared plus 1 is equal to secant squared. So that's a relationship that we can remember. And let's go forward and see our question again. So our relationship was that tan squared plus 1 is equal to secant squared of x. All right, so I want to see, maybe I can use it, or at least it looks hopeful, right? There's tans and secants there's tans and secants in my formula. Now, one thing I could do, one option, would be to move a couple of the tans and make them secant. So it would be like tan to the power of 1x, and then a bunch of other stuff in terms of secant. That's one option. The other option is I could move some of the secants over to become tans and have like a secant squared and a bunch of stuff in terms of tans. So I don't know which I should convert. Should I convert the tans or should I be converting the secants? So when I'm trying to decide between these, and if you don't want to do this preemptively, you could just try one and try the other and see which happens to work out. But I'm going to try to analyze it. What I want to do is I want to have my end result be something I can apply a u sub on. And I remember this, that the derivative of tan is secant squared. So if my final answer is a bunch of tan stuff and then a secant squared, I can say it's a bunch of u stuff du if I make that substitution. So for me, it makes sense to be left with a secant squared and then everything else be tangents because the derivative of tangent is secant and not the other way around. Excuse me, the derivative of tan is secant squared. All right, so let's try that. I'm going to make one manipulation, and maybe to make it super clear what I'm doing, I'll write an intermediate step. You don't have to do this, but I'm going to break out this secant to the fourth as secant x squared times secant squared x dx. So I've sort of taken these two terms here and I've expanded them out a little bit. Now what I'm going to do is I'm going to use one of those two secant squared terms, and I use this formula over here, and I'm going to convert it. So what do I get? The tan cubed out the front, that remains the same. The secant squared is going to then become a tan squared x plus 1. And then all of this is going to be multiplied by my secant squared x dx. All right. I can do a little bit more cleanup here. Maybe I'll combine some of my factors here. I'll say this is looking like a tan to the fifth x plus a tan to the cube x. And then all multiplied by my secant squared x dx. And notice how good this is. What we have is exactly the situation we wanted, where I can come along and make a little u sub, like say u equals to tangent of x. My du is going to be equal to secant squared x dx. We have to remember what our derivatives of these trigonometric terms are going to be. And then it substitutes in really nicely. This is just the integral, well, tangent is u, so u to the power of fifth, plus u to the power of 3, and then secant squared dx is just du. And of course, this is just some power rules. I know how to do that. I got a little bit of space remaining. This is u to the 6th divided by 6 plus u to the 4th divided by 4, all plus c. And my final step, as always, is to substitute in for my u, and that gives me tangent to the 6th of x divided by 6 plus tangent to the 4th of x divided by 4 plus c. So the final point that I'll note about these trigonometric integrals is that often the path forward is not completely obvious. Often it requires a little bit of experimentation or perhaps some clever guessing. So in this case, we sort of guessed that it was going to be the tan squared plus 1 equals sec squared relationship because there's a whole bunch of tangents and secants inside of it. So that was a reasonable guess. But even with that reasonable guess, there was a couple different pathways that we took, and we either had to anticipate what the right u sub was going to end up being, doing it kind of in our heads, or if we didn't want to do that, we could just write down a few of the possibilities ourselves and figure out after writing them down whether there's an obvious u sub that works or doesn't. So the one thing to keep in your mind here is don't feel badly if you try a couple trig subs and they don't end up being helpful. That happens all the time. There's not one linear path here. Try a bunch of trigonometric manipulations and maybe the obvious one works, or maybe there isn't an obvious one, or maybe it doesn't and you have to go and try a couple ones. And in fact, really cleverly well-designed questions are ones where the first obvious trigonometric substitution doesn't work out, but maybe the second or the third one that you do does. So sort of stick with it, keep trying things, writing things down, see whether you can get u substitutions, and that's the methodology for these trigonometric integrals.